complementary counting. So the principle is, instead of counting what you want directly, count what you don't want and subtract from the total. So here we have a simple example. How many passcodes have at least 1, 3? So passcodes from the previous problems are 3 digits, and each digit is from 0 to 9. Well, instead of counting at least 1, 3, it's not really easy to directly count it using our fundamental principle from before. So instead of counting it directly, we say this is total passcodes minus the passcodes without a 3. So the total passcodes, well, we think of our fundamental theorem, our fundamental principle, with each digit as our events. We have 10 choices for each, 0 to 9. We have 1,000 over here. Passcodes with no 3, well, we did that previously in the other video. That was 729. So we subtract the 2, and we get 271 as our answer. So now, when do you know when to use complementary counting? So the first hint, and the hint that really gives away this problem for complementary counting, is this words at least. The words at least really demonstrate that you need complementary counting. Another counting thing is you should use this for when they say triangles with positive area. There's a lot of problems that deal with triangles with positive area, like as you especially go to more high school math. So it is good to use this kind of technique for that. Other than that, it's mainly when you're kind of stuck with directly counting it and you need a better way to do it. Alright, so here's a brief discussion of subsets. So subsets are pretty common to count. So what are they? So first we define a set. It's just a collection of objects. This is the set of the numbers 1, 2, and 3. Simple enough. A subset is a part of this collection. So for 1, 2, 3 we have 8, 1, 2, 3, 1, 2, 2, 3, 1, 3, 1, 2, 3 itself, and this. So this is the null set, which is the set with nothing in it. And this is a subset of all sets. So why is this important? Well, there's a few things we should talk about when counting subsets. So there's one main formula. So for a set with n elements, we have 2 to the n subsets. So why is this true? So say we have our set S, and it has our elements. So we have element number 1, element number 2, element number 3, all the way to element number n. Well, now let's say we're creating our own subset. So we have our subset, and we have some elements. So for each element, we can say E1, we can say we want it or we don't want it. For E2, we can say we want it, we don't want it. For each element, we have 2 choices when we create a subset. We can either include it or not include it. So we have 2 options for our event of choosing E1, another 2 for our event of choosing E2, and so on, until our event of choosing En. How many factors of 2 are this? These are n factors of 2, which becomes 2 to the n. So now a quick application of this. We have a problem from the AMC. And the problem is, how many subsets of set of numbers from 2 to 9 have at least one prime number? So what do you notice about this problem? Well, there's that keyword at least, which tells us complementary counting. So let's do that. The total will obviously be the total number of subsets in this. And since we have 8 elements, because you have to count carefully, our total number is 2 to the 8th. Now how about no primes? Well, if there are no primes, then the only elements it can be have to be 4, 6, 8, or 9. These are the only numbers you can include. And don't you agree that all subsets with no primes are basically a subset of this, right? They're just a collection of these elements. They contain only that. And the number of subsets of this is 2 to the 4th. So this is our answer. We just do solve it numerically. 256 is 2 to the 8th minus 16. And our answer is 240.